The following type of question is called Chinese remainder theorem because some ancient books on mathematics written by Chinese had such questions. Like it says, oh, here's a number. I won't tell you what it is, but I can tell you that if you divide by 2, the remainder is 1. If you divide by 3, the remainder is 2. When you divide by 5, the remainder is 4. Okay? And then it might ask you, like, what is the smallest number that would satisfy these properties? Or like here, how many 3-digit numbers have the following property? Stuff like that, okay? So what this is saying is you're trying to solve for x, whereas x is congruent to 1 mod 2. X is congruent to 2 mod 3. If you divide by 3, the remainder is 2, right? And if you divide by 5, the remainder is 4. So if you have a single number x where it's given its modulo with different numbers, okay, and the number should be pairwise pairwise coprimes. Okay, so they shouldn't. Each of these shouldn't share any common factor. Okay, so in that case, the Chinese remainder theorem says that you can always solve such a thing. Now, of course, there are cases like if you have x congruent to 1 mod 2, and x equals to congruent to 0 mod 4, there is no such x because this second one is saying that x is divisible by 4, right? Which means it's an even number. But if x is congruent to 1 mod 2, that means x is an odd number, right? And therefore, you can't possibly have a solution to both of them. And the reason that you don't have a solution, I mean, you have examples like this is because 2 and 4 share a common factor of 2, right? Yeah. So since 2 and 3 only common factor is 1, 3 and 5 common factor is 1, and 2 and 5 common factor is 1, in this case, you can definitely find an x that satisfies all of them. Okay, that's called Chinese remainder theorem. Okay, but how do you actually solve them? Well, you solve them pretty much like how you solve the Diophantine equations. You interpret what this means. This means x is like if you divide by 2, there's some quotient and you have plus 1, right? And then you take that and put it into the next congruence class. Okay, so you say 2k plus 1 is congruent to 2 mod 3. And then subtract 1 both sides, you get 2k is congruent to 1. But in mod 3, if you multiply both sides by 2, you get 4, but 4 is congruent to 1 in mod 3, right? So you get that k is congruent to 2 mod 3. Then you interpret this again. You interpret this again and say, oh, that means k is equal to 3 t plus 2. Right? If you divide k by 3, there's some remainder, and 2 is there is some quotient, and 2 is the remainder. That's what it means, right? And then you take this and plug it back into your x, so that x is now 2 times 3t plus 2 plus 1, just like that. And that gives you 6t plus 4 plus 1 is 5, 6t plus 5, right? And then because the last one says x is congruent to 4 mod 5, you put that back into 6t plus 5 congruent to 4 mod 5. Okay. Well, mod 5 is 0, right? So we don't need that. And because 6 and 4 are both divisible by 2, oh, actually this is even easier. See, 6 is in mod 5, what's that? 1, right? So you just get t congruent to 4 mod 5. Okay, that just got solved automatically. But this means that t is equal to 4 times some q plus, no, sorry, 5 times q, because it's mod 5. If you divide by 5, so there's some quotient plus 4. And that has to be plugged back in here, so that gives you x equals to 6 times 5q plus 4 plus 5. That's 30q. 6 times 4 is 24, plus 9 is 29. And this seems to say that 29 is the smallest positive number that will satisfy all three properties, right? So indeed, if you mod by 29, that's an odd number, so if you mod by 2, it's going to give you 1. If you divide by 3, well, closest one less than 29 is 27. 27 is divisible by 3, and you have a remainder of 2. And if you divide by 5, 5 times 5 is 25, and 29 minus 25 is 4. Okay, so that gives you, that's going to give you the smallest number. That's how you solve any Chinese remainder theorem type of problem. Okay, so the theorem itself only guarantees that you have a solution, but to actually find the solution, you just have to keep solving one, plug into the next, solve it, and then plug it back into how the x is defined, and keep doing that. And it doesn't matter if you have 3 of them, you can have 4 of them, 5, as long as all the conditions have these numbers pairwise co-primes, then you will always find the solution. Okay. All right. So now to address the actual question, how many 3-digit numbers have the following property? Well, unfortunately, we have to figure out what's the smallest number that this would be. That's a 3-digit number. So if you had like 30, so when q is 30, what do you get? Then you get x as 30 times 30 is 900 plus 29, right? Okay. So I think if you do q equals to 33, that's going to give you x equals to 33 times 3 is 99, so 990 plus 29, which is equal to 1019. Okay. So that's going to be the smallest number. Oh, no. That's going to be, sorry. 32, that's going to, we said 3-digit number. This is 4-digit. Okay, sorry. So this is going to be 960. So 989. That's the biggest Q that will give you 3-digit number. So I was saying to find the smallest number, but no. Okay, so this gives you the largest 3-digit number. For the smallest Q, to make this 3-digit, what should Q be?
3?
3, right? 3 times 30 gives you 90. 90 plus 29 gives you 119, right? So gives you x equals to 90 plus 29, which is 119. So that's the smallest one. So 3 through 32, how many are they? It's, see, 1 through 32 is 32 numbers, right? So q equals to 3 to q equals to 32. Those are the numbers. And if you have 1 through 32, there are 32 numbers, and 1 to 2 are 2 numbers. Well, if you take this away from here, then you get this, right? So 32 minus 2 is what you need, and the answer is 30. Okay?